All right, guys, let's get started. Let's get started. Okay, I want to see your faces. If at all possible, I want to see your faces. I got to see you because I read a lot off of what you guys do. So turn on those cameras. Turn on those cameras. I don't care if you're bathed, unbathed. I don't care. Just, I want to see you guys. You're in class. You're in class. Can you hear me? So if you hold down your space bar, that'll let you talk and then release. Because we're going to do this as much as like in class as possible. Can you hear me? Yes. Oh, good. We're getting some feedback. That's awesome. So let's try that again. Can you hear me?
Yes.
Okay. Can you guys see, this coordinate system here? Kind of. It's a little bit blurry. It's a little bit blurry because this is impossible. I'm making a video with the iPad also that I'll put up for you guys. I'm hoping that again, the more I can see your faces, the better this will be. I'm hoping that as I talk to you, you guys will be able to follow more. Like for example, if I say, okay, we've got this vector A, that's an element of V. Does that help you like actually see it? As I say the words, does that help you see it?
Yes.
I've got A, that's a, help me out. I've got the vector A, that's an element of V. So you see, we can do this. It's not great. I mean, I get it. We're on a raft. It's kind of like we're in this raft and we're setting out to sea. And we're going to see how much water we take on immediately. We're on the Kon-Tiki. Say that.
We're on the Kon-Tiki.
We're on the Kon-Tiki. Say that.
We're on the Kon-Tiki.
You're like, what the hell's the Kon-Tiki, Dr. Warren? Well, these guys from the Netherlands set out in the 1950s to say that the Polynesians actually came from South America. That they rode a raft over, and that's how that area got pollinated. What the hell am I talking about? That's how that area got populated. That's how that area. But they rode the trade currents, and that's what we're doing. You guys are going to be seasick. Say that.
We're going to be seasick.
Yeah, some of your mouths aren't moving. Say that. You're going to play. You have no idea how close I am to the camera right now. My nose is like 1 inch away from the camera, as frightening as this is. Okay, so here we go. You ready? You ready? Again, the more I can see you, the better. Are you ready for this? Say, set sail.
Set sail.
Okay, here we go. All right. Let's go back and see where we're at. How many people watched the video? Okay, there were 4 people in class on Friday. 4 people in class. Cameron, okay. There were 4 people. How many watched the video? How many people watched Friday's video? Okay. How many people still need to watch the video? Okay. Good. None of us. Okay. Watch the video. Okay. So back here. This is going to be so bizarre. But I'm going to get comfortable. You're going to get comfortable. It's going to be bizarre, but we'll get into a rhythm. I mean, heck, if in World War II, kids can go to school and the place is getting bombed, you guys can learn over Zoom. Do we agree? And I can teach to a camera, okay? This is so much better than in March. Oh my gosh, to actually see human beings while I teach. I mean, let me give you, I'm a little afraid I'm going to break the $1,000 camera they gave me, but I want to show you. See, that's you back there. You're on that board there at the front of the room. And then I'm right here. Let me just say, can you guys see that? Can you see this here? Oh gosh, I think I've got it crooked. I knew better than to touch it. So there's there. I think that's. Can you see here? Can you see that there? These are my guidelines. Okay, here we go. Woo! Here we go. Okay, A is an element of V if and only if A is equal to A. I'm not moving until you move. You answer. An ordered triple of 3 real numbers. So what would those numbers be? What do you want to, not mean in general. In general, this would be a
A1.
A1, this would be
A2,
A2, and this would be A.
A3.
Okay, so that's what we have. That's what we have. We've got this A1, A2, A3. Now, in the video, did we talk about the norm? I'm ADD, so you have to remind me. Did we talk about the norm of A? Like if I've got this vector, here, and this blue vector, how to find the length of the blue vector? Did we talk about that? Was that in the video?
Yes.
Okay, so how would I find the length of this vector? Or we call it the what? We call it the what?
The norm.
The norm. If I wanted to find the norm of this vector, I've got these three real numbers. What's the flashcard for that? Anyone?
Square root of A1 squared plus A2 squared plus A3 squared.
Okay, you're not going to be like my daughters. Okay, when I say talk, you.
Oh.
Okay, good. That's one person. When I say talk, you.
Talk.
I'll scream right into the microphone. When I say talk, you.
Talk.
Okay, good. When I say talk, you.
Talk.
Damn it, Dr. Warren, I'm cutting you out now. You can't control me. When I say talk, you. Stand up. I can tell you're already, and you're out there on the raft. Stand up on your raft. Stand up on the raft. Okay, you can't make yourself infected. Slap your face. Say, wake up, man. I'm on a raft. I'm on my 237 raft. Okay, sit back down. Okay. Out of all the vectors in three-dimensional space, and how many vectors are there in three-dimensional space? Infinitely many. Out of all the vectors in three-dimensional space, if I was going to pick the three that are most important, it would be these three. And let me show you. I've got my coordinate system over here. Now you guys can help me out. I guess I need to stay this way. What's that axis? What axis is that?
Y-axis.
The y-axis. What axis is that?
Z-axis.
Z-axis. And which axis is this?
X-axis.
The x-axis. Am I off the board there? Can you guys see that?
Yeah,
You can see everything.
Okay. Cool.
Yeah, that's good.
There. Okay. Is it the right way? Is the camera? Is it backwards? Is it flipped? Is it mirrored the wrong way? Is it look like you're in the room? Okay. Except with myopia, right? I mean, I can't see. Everything's blurry. Okay, so we've got this. If I was going to pick the three most important vectors in three-dimensional space, it would be these vectors. It would be this vector of length 1 that goes straight up the z-axis, a vector of length 1 that goes straight down the y-axis, and guess what the third vector would be. The one that goes down length 1. So all of these are length 1. All of those are length 1, and they go down the axes. Okay, now if I move this guy here, still the same length. I'm not in the picture. Still the same length, still the same direction. Is it the same vector? Is this vector the same as that vector? Is this vector the same as that vector? Yeah. It has to be by the algebra we defined. It has to be. So, but I like to think of these guys. I think of this vector here. I think of this vector right here as being I. The vector I. The one going down the x-axis is I. The one going down the y-axis is J. The vector J. And the one going up the the z-axis is Take a guess. Okay, so I've got these vectors I, J, and K. Now you're a vector if you're an ordered triple of three real numbers. I want you guys try to find the ordered triples that would represent the three most important vectors in three-dimensional space. So you guys at your seats, try to find the three vectors that would represent the three most important vectors. Try to find the ordered triples that represent those. Okay. What do you think for j, guys? What do you think j would be? It's a vector. What do you think the coordinates of j would be? The components of j?
0, 0.
0, 1, 0. Because we're not going at all down the x-axis. We're not moving up the z-axis. We're just moving one down the y-axis. So this is in fact perfect, 0, 1, 0. How about this guy? How about that guy? How about I? What would I be?
1, 0, 0.
1, 0, 0. And finally,
0, 0, 1.
0, 0, 1. 0, 0, 1. Now you're like, Dr. Warren, why are these the most important? Say that.
Why are these
And
not-
these are supposed to work.
I can see the enthusiasm. I can hear the enthusiasm. Watch this. I was playing with this earlier. I can pretend like I'm Superman, and I'm not real athletic. But watch. Just watch. Did you see that? Did you see that? Did you see me flying through the... Like I was just... Okay, now you're awake. Oh my gosh. I turned on my phone for 1 second. Oh. Never mind. Sorry. Let me turn that off. Okay, here we go. What happens to a dead body? Like, Dr. Warren, seriously? What happens to a dead body?
Decomposes.
It decomposes. And these vectors, I, J, and K, are the most important because we can decompose any other vector into them. You're like, Dr. Warren, what are you talking about? These are kind of like the basic building blocks. In fact, we call them a basis. Say that.
Aces.
Somebody didn't say anything. Say that.
Basis.
Basis. These are the basis. These are the basic building blocks that we can use to build any other vector. Like, give me a vector.
1, 2, 3.
1, 2. Okay. I like our creativity. 1, 2, 3. How many real numbers are there? Real Dr. Warren, there's even a minute. But I like this. 1, 2, 3. Somebody didn't even say anything. Like, okay, I'm gonna let everybody else do the work. He can't tell. He can't keep all our bases in his head. Okay. What I want to do is, now you guys are going to sing this like a choir. I want to decompose. Who gave me this vector? What's your name? Red?
Red.
The R vector. Okay? The R vector. Ret. Okay? Ret gave me the vector. Okay? This is Ret's vector. Okay? What I want to do is I want to decompose. Say that.
Decompose.
Decompose Ret's vector. Say that. Now here comes the big word. Into a linear combination. You got to be kidding me. Why is my phone going off? Okay. Okay. Into a
Linear
combination of my three basis vectors, I, J, and K.
basis.
Some of your mouths aren't moving. Into
Basis vectors I, J.
Okay, so now I'm going to say this again. We're going to decompose Ret's vector into a, what's the big new word?
Basis vector.
Linear combination of the basis vectors I, J, and K. And by linear combination, what we really mean is scalar multiplication and vector addition. Scalar multiplication and vector addition. We're going to use scalar multiplication and vector addition to decompose Ret's vector into a linear combination of my three basis vectors I, J, and K. Now let's figure out how we can do this. I want to represent Ret's vector as some scalar times I plus some other scalar times J plus some other scalar times K. And so what I want to do is I want to find three scalars that I can multiply times I, J, and K so that I can get Rhett's vector. I can get Rhett's vector. What do you guys think? What do you guys think? What might the scalar be that would go, we'd put in front of I? Well, if we made this 1 times I plus 2 times j plus
3.
times k, what I want you to do now is I want you to use the definitions that you guys created, use the scalar multiplication that you guys created, and use the vector addition that you guys created and see what you get. Blow that out right now at your seats. It'd be much easier if you're looking at what you're doing instead of looking at what I'm doing. See, it's so nice I can see you guys. It's just so nice I can see, oh, you need a little more time. That's okay. In a video, I just be blah, 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 blah. Do this, blah, blah, blah. I'm still videoing this, so you guys still will have the video version. Unfortunately, in the video version, the camera right here is going to be kind of in a little bit, but I still think it'll be fine. Okay, for sake of time, this would be 1 times the vector, this would be 1 times the vector, this would be 1 times the vector,
1, 0, 0.
1, 0, 0, plus 2 times the vector, plus 2 times the vector,
0, 1, 0.
0, 1, 0, and we got it, Dr. 1, we got it, plus 3 times the vector, plus 3 times the vector, 0, 0, 1. By your definition of I, J, and K. You guys define them. Okay, now, how do we do scalar multiplication? What's our definition? If you have alpha times a vector A, what do we do? How do you do scalar multiplication, guys? How do you do it?
Distribution.
Yeah, pretty much you're distributing across our basis vectors. Oh, okay. So it'd be the vector. Come on, we're taking little steps. We're paddling with our raft. This is alpha times
A1.
A1.
Alpha times A2.
Alpha times A3.
Alpha times A3. So from here, I would get 1 times, I get 1 times, I get 1 times, I get 1 times. I'll keep badgering you. You'll answer. 1 times, 1 times,
0.
1 times,
0.
0. And so we get the vector 1, 0, 0. Here we get the vector, here we get the vector, here we get the vector
0,
0, 2, 0. And here we get the vector 0, 0, 3. Now, how do we do vector addition? How do we do vector addition? How do we do vector addition? You missed me, didn't you, Gordon? You missed me. I can see it. How do we do vector addition?
Add the components.
Add the components. So let's just add the components across. I have 1 plus
0.
plus
0.
0. So using vector addition twice, that would be 1. I'd have 0 plus
0.
0. And then I think you guys get the last one. 0 plus 0 plus 3. So I'm going over here. Can you guys see here? Can you see there? Can you see that? Okay, so imagine I've got this. And I want to decompose the vector 5, negative 2, 7 in terms of the basis vectors I, J, and K. Write down what you would have. Decompose the vector 5, negative 2, 7 into the basis vectors I, J, and K. Okay, now I can ask somebody what they got, because now I can see your names. You know how nice it is to have everybody in class? You know how nice it is to see everybody and not Z-Day, A-Day? Ellie, what do you got for me? Ellie, what do you got for me? Ellie? Cosmo, what do you got for me? Cosmo, what do you got for me?
5i minus 2j plus 7k.
Perfect, Cosmo. Let's give it up for Cosmo. Come on, let's give it up for Cosmo. I want to see those hands. All right, good. I'm sorry, guys. This is so bizarre. I know it is, but guys, I'm teaching to. I'm teaching to you, but I'm teaching to this. But we're going to get used to it. We're going to get used to the Kontiki. We're going to get used to the Kontiki. Okay, stand up again. I need you to stand up again. Stand up. You need to wake up. Stand up. Stretch. Stretch. Get up. I know this requires a lot of effort. Stretch. Stretch. Okay, sit back down. Sit back down. Okay, now what we're going to do, guys, is we're going to take a little adventure that's not going to feel like it's in Calc 3. It's going to feel kind of like we're going back to high school. But what we're going to do is we're going to derive, not me, you. You're going to derive one of the most important results for this class. And it goes back, it relies on right triangle trig. So I'm going to come over here, and I'm going to draw a right triangle. And I'll use this as a motivation. Imagine that I've got the ground here. I've got the ground here, and I've got some beam that I'm going to bolt into the ground, and it's going to go up. It's going to go up, let's just say 27 feet. The length of this is 27 feet, and I know I wanted to make, I know by what the engineering specs had, I know I needed to make a 32-degree angle with the ground. I know it needed to make a 32-degree angle with the ground. And what I want to do is I want to come over here and put a support column in. Put a support column in that's directly perpendicular, carrying that weight. Okay, so one of the things I want to know is, first of all, how long to cut my support column, and then what's the distance from this joint to where I set this column. So try to figure that out. I mean, I don't need numerical answers, but I need some kind of expression. Try to figure out how you could possibly find those distances to tell your excavator where to dig the hole, to tell your metal worker how long to cut that beam. Okay, again, for sake of time, how tall should this beam be, guys? What would represent how tall that beam would be?
27 times the sine of 32.
Perfect. 27 times the sine of 32 degrees. 27 times the sine of 32 degrees. And how long would it be from this joint to this joint?
27 cosine 32.
27 cosine of 32 degrees. Now I should ask, as a mathematician, why? Why is it 27 times sine of 32? Why is it 27 times cosine of 32?
Because of trig.
Because of trig, okay? Specifically, if you've got a right triangle, this is theta, this is your hypotenuse, this is your opposite side, and this is your adjacent side. Hypotenuse, opposite, adjacent, theta. We know that sine of theta is equal to, by the way it's defined in trigonometry, sine of theta is equal to
Opposite over hypotenuse.
opposite over hypotenuse. So then the opposite side, just do a little bit of algebra. The opposite side would just be equal to the Just do a little bit of algebra. The opposite side would be equal to the hypotenuse. Take this guy to the other side. The hypotenuse times the sine of theta. And similarly, cosine of theta is equal to, I don't know why this teaches. Cosine of theta is equal to adjacent over hypotenuse. So the adjacent side would be equal to, the length of the adjacent side would be equal to the hypotenuse times the cosine of theta. Do you think this is important at all in like engineering applications? Do you think this is important at all? Just wondering. Okay, so now, okay, I guess I should put this in here. We're not going to use it today, but just to tangent of theta. What would tangent of theta be equal to? What would tangent of theta be equal to? What would tangent of theta be equal to? I'll keep going until you answer. So tangent of theta. Yeah, it would be my opposite. It would be my opposite over my adjacent. My opposite over my adjacent. Okay, stand up again. Stand up again. You gotta stand up. You gotta stand up. Stretch. I need to reset your brains. Stand up. Dr. Warren, I don't want to stand up. Stand up. Stand up. David, I can see you. Stand up. Alexander, I can't see you, but I wish I could. Josh, did you leave me to go get a beer? Josh. Okay, sit back down. Dr. Warren, was this what we're going to derive? And the answer is no. This is the result we're going to derive. And this is vital. This result's vital to this class. Okay, what I have is I've got an arbitrary triangle. And I know the length of this side is A. I know the length of this side is A. And I know the length of this longer side from here to here is B. And they also gave me the angle between. They also gave me the angle between the side A and the side B. And my job is to find the length of the side that finishes the triangle. I want to find that side C. Now, does it make sense if they give you the length here, they give you the length there, and they give you the angle in between, that you should be able to find C? That you should be able to find C. So go at it, try it. You try to figure out a way to represent C in terms of A and B in trigonometric expressions, potentially of theta. Have at it. And if you guys are watching on the video, you should be going after it too. You don't think I can see you, but I can see you. You should be deriving this also. What time does class end? What time does class end? 11. What time is it now? 10:15. So you have 45 minutes left of the misery. 45 minutes left. It was bad enough in class, Dr. Warren. It was bad enough in class. Now I get video you. Okay, wherever you're at, hold it up to your camera. Whatever you got, hold it up to the camera for me. What do you got for me? What do you got? 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 Stuart, hold it up, Stuart. What do you got? Okay. All right, you can put it down. You can put it down. So what do you guys think? What might be a good move to do? To start this, what might be a good move to do? I mean, if you're trying to figure this out, what do you guys recommend?
Maybe find like the height
I love that.
in a triangle and then go down.
I love that idea. Let's look at the altitude. Say that. Might as well teach some geometry. What word did I use? Altitude. The altitude of that triangle. We put that in there. A is like the what of this triangle? A is like the what of this triangle? The hypotenuse. Could you give me an expression that would represent that height, that altitude, how long that would be? Could you give me a trigonometric expression that would represent how long this would be?
A times the sine of theta.
A times the sine of theta. So if I'm looking at this distance is A times the sine of theta. Now how about this distance from here to here? Again, we're in that same right triangle. How about that distance? What would be a trigonometric expression that would represent that?
A times the cosine of theta.
A times the cosine of theta. Now, I don't know who said find the altitude. Is there another right triangle? Is there another right triangle other than this right triangle? You're like, well, Dr. Warren, it's kind of, he has a cousin over here. This right triangle right here. I want to find C, but I know this leg is A sine theta. What would represent the distance of this leg? This bottom leg. If this is B, and this is A minus cosine A. No wonder you guys look confused. I should always know I'm wrong. That's not a minus, that's A times the cosine of theta. That's A times the cosine of theta, my bad. What is this? So then what would represent this distance? What would represent this distance?
B minus.
B minus
A times
cosine
the
theta.
Okay, now what I want you guys to do is use the Pythagorean theorem on this right triangle and find an expression that represents C. Or at least C squared. Find an expression that represents C squared at your seats. And if you can, simplify. Find an expression that represents C squared. Again, I hate to stop. I mean, you keep working, but now I'm going to just start moving for the sake of time. Using the Pythagorean, English is coming, I promise. Using the Pythagorean theorem, I would have anyone?
Sine theta.
A sine theta squared plus,
B minus A.
and I got to put parentheses around this, B minus A cosine of theta squared. This one's not so bad. This one's just A squared sine squared theta. Plus, now if you guys wrote down B squared plus A squared cosine squared theta and forgot the middle term, I'm going to vomit onto this camera right here. Okay? There's the middle term. There's the middle term. When you blow this out, this should be, it starts with a B. This should be
B
B
squared
squared and then
minus 2AB.
minus 2AB cosine theta. Then plus
A squared cosine squared theta.
cosine squared theta. A squared cosine squared theta. You're like, well, Dr. Warren, this looks like a pretty messy thing to memorize. This looks like a pretty messy thing to memorize. But if you look at this, we've got an a squared sine squared theta, but we also have an a squared cosine squared theta. So I bring those guys together and do a little bit of algebra. I'll get out of your way and I'll talk, because I know it's blurry. I would have a squared times sine squared plus cosine squared, plus b squared minus 2ab cosine of theta. But what is the, like, number one trigonometric rule? If you had to pick one of them, out of all the trigonometric identities, what's the number one?
Sine squared plus cosine squared equals 1.
The number one. Okay, sine squared plus cosine squared equals 1. So this is just, that's just 1 for any angle. So we find that c squared is equal to a squared plus b squared. You're like, holy hell, Dr. Warren, that's the Pythagorean theorem. Minus 2ab times the cosine of theta. And this is our law of cosines. This is our law of cosines, which is really important in this class. That c squared is equal to a squared plus b squared minus 2ab times the cosine of theta. And this is a flashcard. That's a flashcard. It's your law of cosines. It's your law of cosines. And I thought, why are we doing this? You don't know. You won't know for a little bit. Can I erase this? Can I erase this? Can I erase this? Can I erase this? You guys have it? It'll be on the video. Okay, stand up again, stand up again. I need some kind of visual thing. Stand up. It's not that much effort. Now I can make you do burpees and jumping jacks, so just stand up. Okay, let's do some jumping jacks. Come on, jump and jack, jump and jack, jump and jack, jump and... Some of you guys aren't even leaving the ground. Your hands are, okay, it's like gym. Okay, sit back down, sit back down. Guys, is this working? I mean, am I making it, man, like, is it working at all? Is it better than a video?
Much better.
Yes, much better.
Like the dialogue going back and forth, does that help you?
Yes.
Yes.
Okay. Then, I mean, I wish I had like a multi-billion-dollar camera and we could just set up I could be Jimmy Fallon, you know, we could have our Tonight Show here. But this is probably about as good as it's going to get, and we're just going to keep working with it. Are you okay with that? Okay. You're like, no, hell no. Okay, we're October 5th. I'm believing. I'm the only person on campus who's believing. October 5th, I'm going to have you right back here. We're going live. Okay. We're now going to define a new product. Like, oh, great. Right now, we have two operations. We have our vector. I'm not focused on this. We have our vector addition, and we have our scalar multiplication. We know geometrically and algebraically how to add two vectors. We know geometrically and algebraically how to take a real number and multiply it times a vector. What's the only difference between A and 2A geometrically? If you have a vector A, what's the only difference between the vector A and the vector 2A? It's scaled by 2. It's scaled by 2. It's just twice as long. How about negative A? How about negative 2A? How about negative 2A geometrically? Flips it over and stretches it out two lengths. Vector addition. We know the geometric. If I have A and I add B to it, where's the vector A plus B? If I have A and I add B to it, where's the vector A plus B? It's the one that takes A to the end of B. It's the one that takes A to the end of B. But what we don't have is some kind of multiplication between two vectors defined yet. We don't have anything relating multiplying a vector times a vector. And that's what we're going to define right now, our first vector product. And we're going to call it, for lack of anything better, A dot B. Say that.
A dot B.
Some of your mouths aren't moving at all. Say it again.
A dot B.
Say it again. A dot B. Now this is what's kind of bizarre geometrically. Typically, if you have something of length times something of length, what would you expect? Think about it. 5 feet times 4 feet. What do you expect? 5 feet times 4 feet. What do you expect?
20 feet.
20 feet.
20 feet. Not 20 feet, but 20 feet
Square.
squared. You expect area. I mean, geometrically, that's what you expect. You expect area. But that's not what this is. We have A dot B, and this is the way we defined it. It's defined to be the scalar A1 times B1 plus A2 times B2 are you done, Dr. Warren? No. Plus A3 times B3. And this is a flashcard. This is a flashcard. Now close your eyes. Close your eyes. Close your eyes. I've got my eyes closed. Okay. What's A dot B? What's it equal to?
A1, B1, B3.
Plus A, 3, B3.
Okay, perfect. Now give me a vector. Give me a vector. Give me any vector. Give me any vector. I heard that 4, 8, 7. Give me another vector. Give me another vector. Give me another vector. 757. Virginia Beach area code. Okay, now what I want you to do is find the dot product. Find the dot product at your seats. Find the dot product of those two vectors at your seats. Is anybody done? Is anybody done? Does anybody have a final answer? What do you have? What's the scalar? What's the scalar?
117.
117. Who had 117? Who had 117? Okay, I look like some stupid German. Okay, I can't raise my hand like that. Maybe that looks normal. Okay, 117. Now let's just, for those who maybe didn't get that, let's just go through. It'd be 4 times, it'd be A1, 4 times 7. I can write it down. 4 times 7 plus 8 times 5 plus
7 times 7.
7 times 7. And now I'm sure everybody from there can get it. I'm sure everybody. We have 28 plus 40 plus 49, and then we get the 117. Is everybody pretty comfortable? Is everybody pretty comfortable on how to calculate a dot product? Now, the geometry of the dot product is really cool, but we're not ready for that yet. We're not ready for that yet. Let's talk about the properties of the dot product. Let's talk about the properties of the dot product. Okay, so that's what we're going to do now. I'm going to prove one of them, and you guys are going to end up proving a couple of the other ones for homework tonight. What did I just say? Yeah, you're going to prove the other ones. You're going to prove the other ones for homework tonight. But I'll prove one of them. This is my first property of the dot product. So here we are, here's my first property. I just want to see how well you can see. What did I just write down? What did I just write down? I'm not saying it this time, I just want to see what did I write down?
Vector A is an element of the vector space.
A is an element of V. A is an element of V. Then this implies that A dot 0, the dot product of the vector with 0 is what? What do you think the result would be? What do you think the result is? What do you think the conclusion is? That A dot 0 is, it's 0. Now, is it the 0 vector or is it the 0 scalar? Is it the 0 vector or the 0 scalar? The scalar 0. So this is kind of fun. A times 0 is
0.
0. Just like kind of in the real numbers, it's however, A dotted with the vector 0 is the scalar 0. Now let's prove this. Let's prove number 1. So this is the way my proof would start. Given A is an element of V, then A's equal to A1, A2, A3, the ordered triple A1, A2, A3, such that A1, A2, A3 are elements of the real number. So there's my first move in my argument. There's my first move. That if A is an element of V, that's what's given to me, then A is equal to an ordered triple of 3 real numbers, A1, A2, and A3. If it's a proof, I've got to provide a justification. If it's a proof, I've got to provide a justification. What's my justification for that? What would be the justification for that? You guys are going to be making proofs like this on our first quest. And the justification is, and I get that you guys may not know right now, but once I say this once, I think it'll be clear from there on. By the definition of the vector space V. By the definition of our vector space V. Okay, so now what we're going to do is we're going to start with this side, and we're going to try to reach that side. We're going to start with this side, and we're going to try to reach that side. So here we go. I would have A dot 0 is equal to A1, A2, A3 times dotted with 0, 0, 0. And if I'm making my justification, this is by the definition of my 0 vector. This is by the definition of my 0 vector, and we'll just say in this case substitution. We'll say substitution. We're substituting in the component form. That's not a theta, that's a 0. But this would be equal to A1 times, this would be equal to A1 times, this would be equal to A1 times 0 plus A2 times 0 plus A3 times 0 by what? What justification am I using to go from this equality to this equality? What are you using, guys? What are we using? The definition of our dot product. So we'll just say by the definition, DEFN, and then we'll just put dot. You can get away with that. By the definition of our dot product. But this is equal to, and this is, I'm going to give you guys a huge advantage over what I would typically do in Calc 3. This is equal to 0 plus 0 plus 0. But now we're using the multiplication property of 0. We're using the multiplication property of 0, that any real number times 0 is,
0.
Okay, now guys, anytime you use a property of the real numbers, I'm going to let you get away with this because you're zooming. You're on Zoom. You can say by ALG, what do you think that's an abbreviation for? ALG, if you had to guess. algebra, and then we'll put that R there. By the algebra of real numbers. You're using part of the algebra that was built for the real numbers. 0 plus 0 plus 0 is
0.
0. Again, we're relying on the algebra of real numbers. And there's our first proof. There's our first proof in Math 237. Here's our first proof in Math 237. Okay, let me get out of the way. Can you guys see here? Can you see this? Can you see that? Yay or nay? Yay or nay?
Yay.
Okay, perfect. Property 2. Read. What do you have? What do you have? It's like I'm the thing from Addams Family. Read. What do you have?
Vector A and the vector B are elements of the vector space.
Okay, I'm given A and B are elements of the vector space. Then this would imply that
A dot B is equal to B dot A.
A dot B is equal to B dot A, which would make that product our dot product. Use words that you learn. Would make our dot product, like Dr. Warney would be a dot product. It would make our dot product. Why is 5 times 2 equal to 2 times 5? What property, guys, is that? The commutative property. We can commute these guys and it doesn't change the result. A dot B is equal to B dot A. I want you guys to prove that for homework. I want you to prove that for homework. You create a proof of that. Oh, shoot. I've got to give myself some vectors. Okay, I've got A, B, and C are elements of my vector space. A, B, and C are elements of my vector space. Implies that A dot B plus C. Now this is fun. We're combining our dot product with our vector. We're combining our dot product with our vector addition. If there was any mercy in mathematics, write down what you hoped that would be equal to. Write down what you hoped that would be equal to. If there's any mercy whatsoever in mathematics, write down what you hope this would be equal to. What would you hope it would be equal to? If it could be anything, what would you hope it would be equal to? A dot B plus C. What do you guys think?
A dot B plus A dot C.
A dot B plus A dot C. This is homework. Now look at me. This is going to take you 15 minutes and about a page worth of writing to actually prove. Well, not really. Not that I now let you get away with algebra of the reals. But it's going to take about 15 minutes to prove this. This is homework. This is also, I'll keep going. Homework. Okay, I can tell you need this. Stand up. Okay. Now do this. Grab your magic lasso. Some of you aren't standing. Grab your magic lasso. Swing your magic lasso. Throw your magic lasso. Wrap up your attention span. Wrap that up. Tie up that little piggy. Tie it up. Okay, now sit back down. Okay, I've got the vector 3, 5, 7. I got the vector 3, 5, 7 dotted with 2, 4, 6 plus 1, negative 2, 1. I've got the vector 3, 5, 7 dotted with the vector 2, 4, 6 plus 1, negative 2, 1. When you're all done, what should the result be, a vector or a scalar? When you're all done, what should the result be, a vector or a scalar?
Scalar.
It ends up being a scalar. It ends up being a scalar. Find that scalar. Find that scalar. And use your distributive property. Use that new distributive property you got. Use that new distributive property you got. If you're done, hold up your answer. If you're done, hold up your answer. If you're done, hold your answer up to the camera. If you're done, hold your answer up to the camera. Oh, I wish I could see that. I'm going to run up here and see what you guys had. I'm now at the front of the room. Let me see other people's. What you got there? Okay. I'm looking at all you guys. What do you guys have? Anyone? What's the scalar? What's the scalar? Anyone?
58.
58?
68.
68. Did anybody else get 68? Did anybody else get 68? Raise your hand so I can. Okay, so let's see how this works for those who maybe didn't get 68. Okay, I mean, using my new distributive property, I know that this vector times this vector plus this vector is this vector dotted with this vector plus this vector dotted with this vector. It's this vector dotted with this vector plus this vector dotted with this vector. Or we distributed our dot product across these two vectors. Now, how do you do the dot product again? Don't look at your notes. How do you do the dot product again? It's, for this one, it would be 3 times 2 plus 5 times 4 plus 7 times 6. And then we got this plus here, and then we'd be doing the same thing. We'd have 3 times 1 plus 5 times negative 2, then plus 7 times 1. Now don't be like Dr. Warren. When I was first doing the dot product, I don't know what was wrong with me, but I always forgot to put the pluses in there. Would that be bad? Would that be bad? Would that be bad? Does the dot product have a plus with it? Does the dot product have pluses with it? So don't be like me. Don't be like me. How many people think they are beginning to understand the dot product at least a little bit, at least moving it around? Okay, there's just a couple more properties. There's just a couple more properties that I want to get through. Any questions? Any questions? Anyone? Anyone? Guys, seriously, stop me when you have questions. I want this to be as much like the class. And you don't need to raise your hand, because, I mean, I just say, put in Dr. Warren. Just push down that space bar and go, Dr. Warren, and I'll stop. Okay? This is an awkward silence. Now I'm going to see if you guys can figure it. I'm going to see how blurry I am to you. Read this to me. Read this to me. Alpha times
A dot B.
A dot B is equal to
Alpha times
alpha times A dot
dot B.
B, which is equal to,
Alpha dot, or A times alpha dot B.
okay, and this is a property, this is a property of our dot product. Like for example, if you have 7 times A dot B, if you have 7 times A dot B, that's equal to whether the 7's with the A dotted with B, or it's equal to A dotted with 7 times B. Let's prove this. Let's prove this. Now I'm only going to prove this first one. I'll let you guys prove the next one. So this is what we want to prove. Okay, so here we go. This is how much chalk I wrote today. This right here. That's how much, and it's all over the board because I'm such an ADD spaz. Okay, I'm up here just breaking everything. Okay, proof. Given. What does that say? What does that say? Given. Okay, you guys help me out. Read to me.
Given.
Of the vector space and
Alpha is an element of the real.
alpha is an element of the real numbers. Okay, let's see if you can read that. Then this is a new word for many of you. This is a new symbol. It's this backwards E that you maybe some of you didn't know it except in like some eye chart. It's a lazy way of writing there exists. And I'm going to use it a lot. It's a lazy way of writing there exists. So now read to me. What do we have? Then there exists A1, A2, and A3 that are elements of the reals. And B1, B2, B3 that are elements of the reals. Okay, this is an S dot T. What does S dot T stand for? Such that A is equal to A1, A2, A3, that order triple, and B is equal to B1, B2, B3, that order triple. Okay, it's a proof, so let me get out of the way. What's my justification? You guys are going to be making proofs like this on our first quest. Why do these real numbers have to exist so that these are the forms of these vectors? What are we using, guys? What are we using? Anyone?
Definition of B.
By the definition of our vector space V. Okay, now we have all our players on the field. Come on out, join us on the football team. Come on out on the field. We're out here on the field. We've got our vectors defined. We've got our scalar alpha. Now what we're going to do is we're going to start with this side and try to march to that side. We're going to start with the left and try to march to the right. So what we're going to have is, can you guys see down here? Are you good? Can you see me? We're going to have alpha times A dot B is equal to, When you have the parentheses, where do you do first? Which operation do you do first? Are you going to do the scalar multiplication or the dot product first by what we have there? Or are you going to do the scalar multiplication or the dot product first? The dot product, because it's inside the parentheses, then this would be equal to the scalar alpha times A1, B1, plus, don't forget the plus, A2, B2, another plus, A3, B3. I'm making a move. What's my justification? What does your instincts tell you the justification is? What's allowing me to go from this line of logic to that line of logic?
Definition of dot product.
By the definition of the dot product. This is D, E, F, N, and then we're just lazy, dot. D, E, F, N, dot. Okay, now we cheat. We go, well, we want to end here. We want alpha times A dotted with B. So what do you think we do with the alpha? What do you think you do with the alpha? Just guess. What do you think you would do with that alpha?
Distribute.
Distribute it, so now I would have alpha times A1 times B1 plus alpha times A2 B2. I'm really doing two steps at the same time. Alpha times A3 B3. I wouldn't let you do it if we were in class, but I'm letting you guys get away with multiple steps of algebra all at once. Then this would be equal to parentheses alpha times A1 times B1 plus parentheses alpha times A2 B2 plus parentheses alpha times A3 B3. I've used the distributive property, I've clearly used the distributive property of the real numbers, and I've used my associative property of the real numbers. But I can get away with in this class by just writing what? You can get away by just writing what? What can you write? I know I'm off the screen, but what could you write?
Algebra of the reals.
ALG, Big Mason, real numbers. Algebra of the real numbers. Talk, Dr. Warren. I will. Okay, but this is equal to the dot product, and I'm in component form. This is equal to the dot product of alpha times A1, comma, alpha times A2, alpha times A3, dotted with B1, B2, B3. I'm taking this step, which has these pluses and these times in it, and I'm breaking it into that form. What's my justification, guys? What would be my justification? And you can't say algebra of the reals because you're dealing with vectors. We have vectors, so it can't be algebra of the reals. What are we using, guys, to go from this line of logic to this line of logic? Are we using vector addition? You're like, well, no, because we would have it like A1 plus B1, A2 plus B2, A plus 3 plus B3. What are we using to be able to go from this line to this line? And this is where these proofs get a little bit more complicated.
Dot product.
The definition of the dot product. So write that down. I'm not writing it down. You write it down. By the definition of the dot product. I'm lying. I am writing it down. So the definition of the dot product. But this is equal to alpha A dotted with B. This is equal to alpha A dotted with B. Oh, and I need parentheses here. Sorry, my bad. This is equal to alpha A dotted with B. And this is kind of hard too. I'll leave it there. By definition of what? You write down what you think should go there. You write down what you think would allow me to justify from going from this line of logic to that line of logic. What do you think it is? Take a guess. What do you think it should be?
Definition of vectors.
By the definition of vectors. By the definition of vectors. Okay. One more property, then I'm freeing you from this misery of seeing me. Guys, you have no idea how happy I am right now. I mean, you really have no idea how happy. In March, talking to an iPad, do you know how hard it is to teach an iPad? The fact that I can see your faces, I can hear you, it just makes this feel more like it should. And I hope for you guys too. I hope even though it's blurry and even though it's awkward. I mean, but you're used to that with me. I'm awkward. I mean, guys, you're in Calc what? What? 3. You're geeks. You might not want to pretend you're geeks, but you're geeks. You might try to hide it so you can like date somebody, but you guys are geeks, whether you like it or not. When you get the answer right in the back of the book, you get euphoria coming on. It's like, oh, you want to show your friends who don't even know math? Look. Like in engineering or any other, look, I got the answer right. And they're like, what's wrong with you? This is math. You're a weirdo. Okay? You're a geek, I'm a geek. It's going to be weird. We knew it was going to be weird. Okay, one last property, then I'm freeing you from this misery. And I guess while I'm erasing, let me talk a little bit. For homework, I want you doing those 2 proofs, the commutative and distributive of the dot product, the commutative property and the distributive property. That's probably 20 minutes. That's probably 20 minutes of work. I want you reading section 12.3. I want you reading section 12.3, and I want you working on the homework, finishing up the homework in 12.2. And if you want, you can start 12.3 homework. You can start 12.3 homework. Okay, last property before the misery ends. This is one of my favorites, and I don't know why. I don't even know what number I'm on. I'm going to call it 6. It's okay, they're just going to be flashcards. A dot A. A dot A. Try to find out what A dot A is. Go ahead, try to find A dot A. In component form. Try to find the real number that represents A dot A. And we got 60 seconds. What do you guys got for me? What would A dot A be? What would that scalar be? What do you got?
A1 squared
A1 squared? Awesome.
plus A2 squared
Don't forget the plus. Don't be like Dr. Warren. A2 squared plus
A3 squared.
A3 squared. That's exactly right. Now, let me ask this. Have we seen this before? A1 squared plus A2 squared plus A3 squared. Have we seen that before? You're like, Dr. Warren, that's related to the norm. What's the norm of A? What's the norm of A? What's that flashcard? The length of A. Help me out,
Square root.
the square root of,
A1 squared plus A2 squared plus A3 squared.
A2 squared plus A3 squared. So this is fun. A dot A is equal to the norm of A. A dot A is equal to the norm of A. A dot A is equal to the norm of A squared. This is such a fun result. A dot A is equal to the norm of A squared. We're going to use this all the time in this class. We're going to use this all the time in this class. I cannot thank you guys enough for coming out and playing today. I'm climbing in the sandbox from wherever you're at. Okay, like again, how many of you are in town? How many are in town? How many people are, okay, like this drives me insane to think you guys are like within a few baseball throws of me. And I've got to see and look at you at a video. I got to see and look at you at a video. Okay, when's our next class? Wednesday. I want to see everybody's face. I want to see everybody's face on Wednesday. So come, cameras open. Come, cameras open. All right, have a great day, guys. Please be safe. And listen to me. If you're here and you got coronavirus and you're still watching this video, You are my hero. I want to be you. I want to be you. I want to be you. You guys are amazing. You guys are amazing. See you guys.
Yeah,
Thank you.
Thank you.
What class what you finished?
This is Calc 3. This is
Okay.
Calc 3.
How's it going?
It's been the idea of like doing it live, zooming it live was terrifying. And you know, but it seems to be working. I mean, unbelievably, it seems to be working. There, I mean, you can kind of see this is kind of what it looks like.
Yeah.
And we're still able, I should have my mask on, but this is kind of like, you know, I'm here, you know, and I can say, okay guys, what is the vector A dot B? And then
That's
they're
actually really nice.
it's not bad. I mean, like in the library set me up with this, and then I'm still videoing with the iPad just because it's they may not the clarity for some of their feeds, and then I'll throw that up on mine. So.
I think that's what we're meeting somebody down here to look at.
Oh, to look
Setting
at
up
to
the
look
camera
at setting up
yeah.
like this. I mean, I was amazed. The chalkboard works better than the whiteboard. With the whiteboard, you get a lot of glare from the lights coming off of it. So the chalkboard actually works.
Nicely.
And then the fact that like they come up on a grid pattern up there where you can see their faces. Because typically when I'm videoing to a stupid iPad.
Yeah.
I'm like, okay, blah, 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 do this. And then I'm like, you're done, you know, but I don't realize, oh, it's taking them a long time. This is brand new to them to have to write this down. You know, because I'm sitting there like, okay, 50 seconds, this is really gonna take, I'm just saying nothing.
Yeah.
But no, for me, I think
like
it's,
your Caucasian plan.
oh, you do, that's pretty cool. That's no, what are you guys professors of?
Anatomy.
Oh, anatomy, okay, that's,
So we're exploring our options too. We have a makeshift setup upstairs, which is pretty good, but I guess